friends, this video on Semiconductors Part 10 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till Part 9 before going ahead with Part 10. So let us talk about the forward biasing of PN junction diode in detail. So what happens when we forward bias a PN junction diode? Let us suppose before biasing the diode, when no external voltage was applied across the diode, there was a potential difference between the P side and the N side, and that potential difference was known as the barrier potential. Let me denote that as V0, or we also call that as barrier height. So let me call that as V0, right? Now, let us suppose when we apply an external voltage, that is when external voltage is applied, say external voltage is V. So what will happen? This is positive side which is connected to P, the negative side connected to N. Now when this external voltage V is applied, these positive will repel the holes present in P, because P side will have more holes, and holes are also positively charged. So when it is connected to positive terminal, it will get repelled from this side and it will start moving. The holes will start moving towards the depletion region. Similarly, if we look at the N side, the electrons will get repelled from the side due to this negative terminal, and as a result the electrons of the N side will also start moving towards the depletion region. Now when the holes reach this depletion region, it will combine or it will recombine with some of these negative charges. Similarly, electrons will combine with some of these positive charges, and as a result, the width of the depletion region, this width will reduce, because some of these charges will get nullified because of these holes and these electrons, right? So the width will reduce, and also the barrier height will reduce. That's because earlier the barrier height was V0, but now due to this movement and recombination of holes and electrons, the potential difference between these two ends will also reduce. So when external voltage is applied, what will happen? Depletion width will reduce, and also the barrier height will reduce. So the barrier height will become, earlier what was the barrier height? It was V0. Now it will become V0 minus V. So it will reduce by V, right? Now if the applied voltage, if this value of V is very small, in that case what will happen? The width will reduce little bit. There will be a slight decrease in the depletion width. Therefore, when the width reduces little bit, little more electrons will be able to pass the junction, little more majority carriers will flow across the junction. As a result, the current will also increase a little bit. Now when the applied voltage is very large, in that case what will happen? The decrease in the potential, the decrease in the depletion width will be very large. So the depletion width will become very less, and as a result the current will increase even more. So that proves that as the external voltage is increased, the current will also increase. So forward biasing encourage the majority carriers flow. That means as you increase the forward biasing, as you increase the voltage, external voltage, in case of forward biasing, your more and more majority carriers will flow across the junction. Therefore, the current will increase. So that means in case of forward biasing, what is happening? Electrons are flowing from N region to P region, and holes are moving from P region to N region. So it is encouraging the flow of majority carriers. So in another way, what is happening? So in another way, we can say that majority carriers flow is encouraged by forward biasing of a PN junction diode, right? So the same thing we can interpret in this way. As I mentioned in the previous slide, since electron is flowing from N to P and holes are moving from P to N, that means what is happening? Electrons are basically injected into P. That means, what does this mean? This means electrons are injected into P region. Similarly, holes are injected into N region. Now, what are electrons in P region? Electrons are the minority carriers in P region. So, we can say that minority carriers are injected into the region. So, this is also known as minority carrier injection. So, what happens when we forward bias a PN junction? When we forward bias a PN junction diode, it encourages the majority carrier flow. Now, when the majority carriers flow from their region of high concentration towards the region of low concentration, it in turn injects minority carriers into a junction. So, that means forward biasing causes majority carriers flow across the junction, minority carrier injection occurs. Both of these mean the same, right? Because majority carriers flow across the junction. That means electron, which is majority carrier in N, it flows from N to P. So this is called majority carrier flow because electron is the majority carrier in N. So it is flowing from N to P. But if you look at it from point of view of P, what is happening? For P, electron is the minority carrier and electron is getting injected into P. So that means minority carriers are getting injected into P region. So this is what you can see here. In the P region, you have the injected electrons, and in the N region, you have the injected holes. Okay. So what is the total current in this case? The total current will be hole diffusion current plus electron diffusion current, because in this, when you forward bias, as I told, it encourages the majority carriers, and majority carriers always diffuse. Diffusion is always related to majority carriers and drift is always related to minority carriers. So in forward biasing will always encourage the flow of majority carriers, and majority carriers always diffuse across the junction. So in this case, total current is equal to hole diffusion current plus electron diffusion current. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.